Hello everybody, Chapter 5, Lesson Delta, Solving Equations Involving Logarithms. Objectives to solve equations involving logarithms, some more, keep solving, do some push-ups, and then keep solving. The one thing with logarithms is when you do solve equations, you must be careful to check for extraneous solutions. So be aware of that along the way. Let's get it started. Okay, so we're going to kind of go over three different levels of difficulty for these solving of equations. Keep in mind your properties of logarithms through each of the problems that we see. So product, quotient, and all the basic properties of logs. So I'm just going to go ahead and start solving, and you try to keep up, and after a while you'll start to catch on here. So let's get it started. So 2 to the x is equivalent to 64, and I can write 64 as 2 to the 6th. Therefore, since both of these are the same base, x should equal 6. Okay, number 2, I'm going to add ln of 3 to the right side. And looky there, same base logarithm, no coefficient on the front, x must equal 3. Okay, let's look at the next one. I know that 243 is equal to 3 to the 5th. Therefore, I could write 1/3 as 3 to the negative 1. Therefore, I've got 3 to the negative 1 to the x equal to 243, which is 3 to the 5th. This would be equivalent to 3 to the negative x is equal to 3 to the 5th. Notice how I'm using my properties in my favor. Therefore, negative x equals 5, so x equals negative 5. Okay, let's keep strolling right along. E to the x equals 7. I have no idea what that is, but I do know if I put this in logarithmic form, the natural log of 7 would have to equal x. Now, I would have to go ahead and plug that in. I would assume that that's probably a little bit more than 2. Let me go ahead and check on my calculator. The natural log of 7, not quite. It's 1.946. So x is approximately 1.946. Okay, how about the next one? I don't know. I can't solve this with my calculator yet, but I can write it in exponential form. E to the negative 3 would equal x. You could write x equals 1 over e to the 3rd, or you could calculate e to the negative 3 comes out to be 0.049. So x would be approximately 0.049. Okay, ln of negative 3. Now, if you punch that into your calculator, you're going to have issues. And here's a reason why. If I write this in exponential form, notice that an exponential function cannot ever equal negative numbers. Okay, if you have a positive leading coefficient on the front of your exponential function, then there's no possible way that you could get a negative output. Okay, so there is no solution. No solution does not exist. Okay, for the last one, this is the common log. If I write it in exponential form, I get this, and 10 to the negative 1 is 1/10. Those are basic level solving problems using some of our basic properties of logs. Let's move on to the intermediate level. Okay, in the intermediate level, let's go ahead and solve. It's just got a couple extra steps added. In the first one, I'm going to divide both sides by 3. So 2 to the x equals 14. 2 to what power gives me 14? Well, I know 2 to the 3rd gives me 8, and 2 to the 4th gives me 16. So I know x will be somewhere in between 3 and 4. I don't know how to do that without my calculator. So I'm going to do the log of base 2 of 14 into my calculator. That should give me x. I'm anticipating the answer to be between 3 and 4. Log base 2 of 14 comes out to be 3.807. 807. Cool. Okay, on the next one, very similar to the last page, I'm going to rewrite this so that I have the natural log on both sides. I have this ability to do that so that now I can set their arguments equal. Now, in this case, this is where we're going to want to be careful for an extraneous solution. So let's see what we get. Looks like I get 4x is equal to 8, so x is equal to 2. Now, I have to check that in both of these and make sure that the solution is a real number, right? So, or the when I evaluate, I get a real number. So I get ln of, let's see, that would be 10 minus 1, which is 9, minus ln of 9. Does that equal 0? Yes, it does. It checks. So it satisfies the original equation. You only need to be careful with logs. With exponentials, you should be pretty good. Okay, let's solve this. Let's add 3 and divide by 2. If I add 3, I get 14, and divide by 2, I get 7. So 3 to the 2x minus 5 is equal to 7. Now, this is kind of sloppy looking right now, and base 3 and 7 don't really tie together very well. So I'm going to do the log of base 3 of 7 and set it equal to the exponent 2x minus 5. So x will equal, I'm going to subtract 5, or excuse me, add 5 and divide by 2. So I'm going to add 5, that'll be log base 3 of 7 plus 5, and divide it all by 2. I would use my calculator in this case, and it does some good work for me. I get 3.386. Outstanding. Okay, let's do the next one. Add 5, divide by 4. So e to the x is equal to 5/4. So the natural log of 5/4 is equal to x. So the natural log of 5/4 is 0.223. We are doing some intermediate level solving. Okay, subtract 5. So 2 ln of x equal to negative 1. So ln of x is equal to negative 1/2. All right, so again, just to reiterate, we never want our argument to be negative. If this is less than 0, we got issues. There won't be a solution. It is okay if a logarithm's output is negative, right? Because if you look at the graph, the range is all possible numbers. It's the domain that's going to be an issue if it's negative, and our domain is our inputs here. Okay, so if the natural log of x equals negative 1/2, then that means e to the negative 1/2 equals x. In exact form, I could say that x equals 1 over the square root of e. And I'm going to leave it like that. You could find it on your calculator as well. Okay, so remember these two things. You cannot ever have a logarithm with a negative input. And the other thing is, when you're working with logs and you're solving, always, always, always check for extraneous solutions by seeing if the values you come up with for your solutions satisfy the original equation. Okay, let's move on to the upper level solving questions, and then we'll call it a day for lesson delta. Okay, first we're going to solve these equations. I didn't give a whole lot of space here. That's outstanding. Okay, I might work them up here. Okay, let's take number 1. Now notice that number 1, if I said that, let's say u equals e to the x. If I said u equals e to the x, I could rewrite the equation below as u squared minus 3u plus 1 equals negative 2. Now wouldn't that be nice if we could just use our ability, oops, that's not a negative 2, it's a negative 1. Our ability to factor to solve this, and that's exactly what you're going to do. So I'm going to factor u squared minus 3u plus 2, which would be u minus 2 and u minus 1. Okay, so to solve that equation, I would say that u has to equal 2 and u has to equal 1. Now, since I let u equal e to the x, then I could say that e to the x, when e to the x equals 2 and e to the x equals 1, those values for x should solve this equation. that means that the ln of 2 and the ln of 1 should be values for x that are solutions to the original equation. Now x equals ln of 2 is a number. It's not a nice number, but it is a number, and the ln of 1 is equal to 0. So I've got two solutions to that equation. Okay, when you see something in this quadratic form, go ahead and do what's called a U substitution, which is that process right there. Okay, number 2. If you look at this equation here, I see all natural logs. Now, what I want to do is I want to condense both sides to the best of my ability. Now, since I see a sum of 2 logs of the same base, I'm going to condense that. So that would be ln of x minus 2 times 2x minus 3. Remember, sum means multiplication. Okay, on the right side, I'm going to condense by bringing this 2 up as an exponent. So it would be the natural log of x squared. Okay, now notice that I've got a natural log on both sides, fully condensed. That means that I can set the two sides equal. Those arguments now have to be equal to make this equation true. Okay, now let's go ahead and expand that left side. That'll be 2x squared minus 3x minus 4x plus 6, which means that is 2x squared minus 7x plus 6. And that's all equal to x squared on the right side. Now we're going to use some more factoring. If I subtract x squared from the right over to the left, I get x squared minus 7x plus 6 equals 0. I'm going to factor. That'll be x minus 6, x minus 1. Therefore, x has to equal 6, or x has to equal 1. Let's check and make sure that neither of these are extraneous solutions. Okay, so if I plug in a 6, I get ln of 4 plus ln of, oh boy, let's see here. If I plug in a 6, I get 12 minus 3 is 9. Is that equal to 2 ln of 6? Well, let's see. Ln of 4 plus ln of 9 is ln of 4 times 9, which is 36. And 6 squared is also 36. So x equals 6 checks. Let's check x equals 1. If I plug in a 1, I get ln of 1 minus 2, which is negative 1. Oh, that right there should set off alarms. That does not exist. Right? You cannot have an input of a negative value, and that would happen again for the second piece. Right? I would get negative 5. Another set of bells and whistles should be going off. And then, of course, here I would get ln of 1 squared, which, of course, would be 0. So we get a problem there. Therefore, x equals 1 is an extraneous solution. We're not going to include that in our solution set. So x equals 6 is our only solution. Okay, a couple application problems, and we'll call it good for lesson D. $5,000 is invested into an account that earns 6.75% interest continuously. How long will it take for the account balance to double? Okay, so what we want to use is account amount is equal to principal balance, which is 5,000, times e to the RT. All right, so we want our account balance to double. So 10,000. Our original balance, 5,000, e to the rate, 0.0675, and we want to know how long it will take. All right, so I'm going to divide both sides by 5,000. And I'm going to have to use my calculator, but before I can do that, I got to isolate t. So I'm going to write this in exponential form, in logarithmic form. So this will be ln of 2 is equal to 0.0675 t. So the amount of time it'll take to double will be ln of 2 over the rate, 0.0675. If I wanted to know the amount of time it would take to triple, it would be ln of 3 over the rate. If I wanted to know the amount of time it would take or for its half-life, I would take ln of 1/2 over its rate. Okay, so please understand that this is kind of cookie cutter in a way, all right? Whether it doesn't matter how much money you start with, as long as you have the rate, you can figure out how long it'll take to double, triple, quadruple, whatever you want it to do. So using my calculator, I'm going to take the natural log of 2 divided by 0.0675, and it looks like it'll take a little over 10 years. 10 years to, it's 10 point, what is that, 269. So 10 and a quarter years in order for that account balance to double. All right, application 2. This will be a fun one. S of t is a function that calculates the average teacher's salary from 1985, which is t equals 5, to 2020, which is t equals 40. Find the average teacher's salary in 2015. Of course, that would be S of 35. Doesn't look like I put S of t on the notes. Kind of crucial to this problem. S of t is negative 1.562 plus 14.584 ln t. So what you're going to want to do is for y1, plug your function in. Now just a reminder, when you're working in your calculator, you don't have t available to you, so you are working in your calculator with x as your independent variable, knowing that it applies to t. By my calculations, using my TI-84 plus, I'm getting an average salary of $50,289.20. Okay, average salary in 2015. Now it also asks us here, in what year was the average teacher's salary $45,000? So based on this model and the fact that the coefficient of ln of t is positive, I can make the assumption that the average salary is increasing. Okay, therefore I'm expecting the year to be some number less than 2015. Okay, so what I would do is I would take 45,000, set it equal to the function, and solve for t. All right, so I'm going to take 45,000. I'm going to add 1.562. I'm going to then divide by 14.584. And I get 3,000. I'm going to make an estimate here. 85.680 is equal to ln of t. Okay, now I might have an issue here, but we'll see. So the natural log of t equals that. Therefore, e to the 3085.680 should be the year. I think I've got an issue here. And the issue is that I should have plugged in just a 45. Okay, so just a 45. Now that, because e to that number is extremely large. Okay, so I'm going to add, I'm going to go back to my original and call that 45. I'm going to divide that by 14.584. This is really good to kind of get used to, but I'm going to get 3.193. That's making a lot more sense to me. Equals ln of t. You should take some context clues when you think about these problems, and when you're working through them. But the year should be given by that, which would be about 24 years, which in the context of the problem, what is that? That's 19 years after 1985, which would be 2004. Okay, so as I went through this problem the first time, e to the 3,000th power is a massive number. So that should give you an indication that something's going on and you're doing something wrong, of which I clearly was. So I hope that solving made sense to you. Let me know if it didn't, and we'll see you in the next video.